All right, the next presentation is going to be on the next column of that table that I've asked you to do. Again, this was going to be a very quick one once you kind of get through the concept of it. I want to explain what it originates from, so bear with me for a little bit. I think that background information is very useful in understanding why this happens. But then I'm going to show you the quick and dirty way of how you can do hybridization very quickly and easily if that is asked on this year's national exam. All right, hybridization is where molecular orbitals form a hybrid orbital with characteristics of each to allow for equal bond energies. So in essence, these s and p and d orbitals, they mash up together, creating an orbital that has characteristics of each, but is altogether of an equal type of energy when they form bonds. So let's look at an example of that. Let's look at the classic example of methane, CH4. So we see the Lewis structure here drawn, CH4 with carbon bonded to the 4 hydrogens. Let's take a closer look at carbon. The ground state configuration of carbon is 1s2, 2s2, 2p2. Okay, again, order of filling, electron configuration, something you need to be aware of, be able to do. Now, something that I don't expect to be asked this year in the national exam would be orbital notation because it just takes too long. But if you look at the orbital notation of carbon, a more detailed picture of this, 1s arrow up and down. Again, the arrows are the electrons. They spin in opposite directions when they're in the same orbitals. Okay, again, that's called Pauli exclusion principle. Then we fill the next orbital of equal energy, of higher energy, off-Bau's principle. We fill the lowest energy orbital, then we fill the next one, off-Bau's. Arrow up and arrow down. And then the 2p's, they come in triple forms, 2px, 2py, and 2pz. There's only 2 more electrons to go. And then we have the last electron configuration rule, Hund's rule. Hund's rule says because all of these are 2p orbitals, they have equal energies. Their only difference is, are they located along the x-axis, the y-axis, or the z-axis? So because they're equal energies, we put 1 electron in each before we double up to minimize the electron repulsion. So this is the ground state orbital notation of carbon. Now the first thing you might ask yourself is, how does carbon even bond 4 times when there's only 2 orbitals that have an electron in each? You'd expect carbon to want to bond 2 times, not 4. So what happens here? Well, actually what happens is one of the electrons from the 2s, when bonding is starting to take place, jumps over and goes into the 2p. Since they're all on the same energy level, the second energy level, that electron jumps over, and now what we have is we have 1 electron in the 2s and 2p, and 1 each in the 3 2p orbitals. Now you can see why it would need or want to bond 4 times to fill up those orbitals and get a total of 8 valence electrons. So when we do dot structures and the 4 corners, one of the 4 corners is the s orbital of its valence floor, its highest row, whatever row it is on the periodic table, 2s, 3s, 4s, whatever floor that element symbol is on. For carbon, that'd be the 2s, and then the 2px, 2py, and 2pz. So those 4 corners really are the highest floor s and p orbitals for that element, its valence electrons. That's what those 4 corners actually represent when these electrons shift and have the number of electrons in each of the total orbitals. Well, if I were to now draw the bonding that takes place between those hydrogens and that hydrogen, each hydrogen has got an electron in the 1s. So one of the hydrogens is going to bond with the 2s orbital, which again is a spherical orbital. And then the other 3 bonds would be a 2p orbital, which is that dumbbell shape, overlapped with the 1s of hydrogen. We have 3 of those. Now, if you look at this picture, do you notice or think of what's wrong here conceptually? What would be wrong with this picture? Well, what we have is an overlap of a 2s orbital with the hydrogen 1s orbital. And then we have 3 where we have p orbitals overlapped with the 1s of hydrogen. We know that because we fill 2s before 2p, we know that the 2s orbital has got a different energy than a 2p orbital. So the bond here, this bond would theoretically have a different or a lower energy than this bond here, which would have a higher energy. And when we look up these bond energy tables, we know the carbon-hydrogen bond is of equal energies. Well, if this was what would happen in the molecule, this could not explain why they're equal energies. The 2s and 1s bond would have a different bond than the 2p 1s hydrogen overlap of the other three locations. We can't have these locations all be different energies. So what happens? What ends up happening is these 2s and 2p orbitals, they morph together, forming a mashup of the orbitals, creating what's called a hybrid orbital. So let's take a look at that next page. So what ends up happening is that one 2s spherical orbital and the three 2p dumbbell orbitals come together to form four equal energy orbitals called sp3. Why sp3? Because there's a single s orbital signified by the upper script. Now there isn't a 1 put there, but theoretically that's what it is. There's a single s orbital and there's three p orbitals that come together, forming what's called an sp3 hybrid orbital. An s and three p's coming together to make a hybrid orbitals. And here's what a picture of it might look like, where we have still the spherical end of the s orbital, some of its characteristic shape, along with part of that p shape, creating a hybrid orbital. So now a sp orbital looks like something like that, where we've got kind of the s end and the p end, but this would be a morphed or mashed up hybrid orbital that has characteristics of s and p all together. So now what really happens is the carbon bonds with the hydrogens, where we have each of these is an sp3 orbital that is now overlapping with the hydrogen's 1s. Now hydrogen doesn't have to hybridize because it only has one orbital, one electron in it. So what's going to happen here is down below is here is the picture of what really happens in real life. The inner shell electrons of carbon do nothing. They're not a bonding pair. But that 2s and 2p now becomes sp3 hybridized orbitals, where we have one electron in each. And each hydrogen is a 1s orbital. So now a bond will form here, where the electrons can now bounce back and forth, filling each other's orbitals, putting two up to the top with carbon or two down below with the hydrogens, where they bounce back and forth. And we form these four bonds, four overlapped areas, where what we have is an overlap of an sp3 hybrid orbital bonded to a 1s orbital of the hydrogen. And that now means, if you look at the picture above in the drawing, all four of those bonds are of equal energy because it's between the same type of orbitals. So that's why hybridization takes place. It's to create bonds that are of equal energies. Now, that's the conceptual understanding of why it takes place. What do you have to know for the national exam? On the national exam, when you look at an element like methane, you have to understand that when you draw the Lewis structure, it has 4 electron domains. Bond, bond, bond. Now, if it's like water, how many electron domains does it have? Not 2. It also has 4 electron domains, because lone pairs also count for electron domains. So both water and methane, CH4, have 4 electron domains. They will have then the same hybridization. So these hybrid orbitals, actually lone pairs will also be placed in them, just like bonds will as well. So once you identify the number of electron domains, so we can have 2 electron domains, 3, 4, 5, or 6. That's the most amount of electron domains you can have. You can't have 1 because that is a diatomic molecule, and a diatomic molecule does not hybridize because there's only one single bond that takes place. You must have a central atom. In order to have a central atom, you must have at least 2 electron domains to be a centralized atom. So if you have 2 electron domains, the hybrid orbitals that form is called an sp. If there's 3, sp2, which means to have 2 electron domains, an s and 1 p orbital, only 2 orbitals hybridize to form an sp. 3 orbitals hybridize to form an sp2, 2 p's and an s. Whenever we have 4, like water and methane, those are called sp3 hybrid orbitals. If it's got 5 and 6, now we have hypervalency. We violate the octet rule. Now we know there's no more. We can't have more than 3 p orbitals on a floor. So now in order to be hypervalent, we must now start adding in the d orbitals. So to have 5 electron domains, we have an s orbital, a d orbital, and 3 p orbitals come together. 5 orbitals come together to create a hybridization that allows us to be able to fulfill 5 electron domains. 6 electron domains, sp3d2 is what we would have. Okay, so once you have the number of electron domains, then we're able to figure out the hybridization. If I add up a single S and a single P, what does it add up to? 2. If I add up a single S and 3 P's, what does that add up to? 1 plus 3 is 4. So if you count up the number of superscripts on the hybrid orbital, that needs to match the number of electron domains. You'll notice that each of these goes from 2 with S and P all the way down to sp3d2, 6 orbitals, should be 6 electron domains. So that's all you need to know. If they ask what is the hybridization of methane, you would say sp3 because it has 4 electron domains. Okay? So that's the quick and dirty of how to figure it out. Now, these hybrid orbitals are the shapes of these morphing together, but for the most part, if they ask that question in FRQ, you're specifically just going to write down what is its hybrid orbital, and that's what you put down. SP, SP2, SP3, SP3D, or SP3D2. Those are the only answers that you could put on the national exam. All right? Again, the column to fill out, these are the only letters and numbers you're going to put down to fulfill that column. Hopefully now it makes sense. If not, again, send me an email. Thank you for listening.